Hello and welcome back to Chapter 8. Today we're going to look at Section 8.6, which deals with solving exponential and log equations. Now, if you think back to other situations throughout the year when we've talked about solving, remember when we go to solve an equation, we are actually going to find a value for the variable. So if you recall back to like sections 8.4, 8.5, when we've been dealing with these properties of logs, one way that we can solve an exponential equation is to use the property that says if two powers with the same base are equal, then their exponents must be equal. So to look at this scenario, we're going to look at example 1. So if you go back and double check your work, we would have 2 to the 4 times 5 is equal to the 32 raised to the power of 5 minus 1, or 2 to the 20th is equal to 32 to the 4th. And you can verify these on your calculator and you'll see that you get a number a little bit over 1 million for both. Now sometimes, like in example 2, we can't always rewrite a power so that the bases will cancel out. So in that case, what we're going to have to do is we're going to have to take a log. Now in the case of example 2, we have 4 to the x equals 15. There's nothing that I can raise 4 to give me 15. Likewise, I can't rewrite 15 so that it's 4 to some power. So I'm going to have to do something else in order to cancel out this 4 so that I can get the variable x by itself. And if you recall, if I take the log with the same base as my power, so in this case log base 4 of 4 to the x, then ultimately this log base 4 and 4 are going to cancel, but I have to take that log base 4 of the other side as well. So this is going to equal log base 4 of 15. Now again, because I am able to cancel out this log base 4 and 4, I'm left with x equals log base 4 of 15. And if you want to get a decimal approximation, then we can go ahead and say that x is approximately equal to, and we'll use our change of base. So we'll go log of the tall, or log of 15, divided by log of the short, or log of 4. And if you type that in your calculator, you'll see that you get something approximately equal to 1.95. Example 3 is similar to example 2. except now we're going to solve when 5 to the x plus 2 plus 3 equals 25. And in this case, if you notice, this plus 3 is not included in the exponent. So the first thing we're going to want to do is we're going to want to move that over to the other side so that we can isolate the power piece. So I'm going to go ahead and subtract 3 from both sides, and I'm left with 5 to the x plus 2 is equal to 22. And now that I have this base by itself, I can go ahead and try to cancel out. And the reason I know I have to cancel out is because I can't take 5 and raise it to some power and get 22, so I can't simplify this side. So the only other thing that's going to cancel out this 5 is if I take a log base 5 of that power of base 5, and that's being raised to the x plus 2. And if I do it to one side, I must also take log base 5 of 22 on the other side. So my log base 5 and 5 are going to cancel, and I'm left with x plus 2 equals log base 5 of 22. And in order to go ahead and solve, we're going to have to go ahead and subtract that 2. So we get x is equal to, and just for ease of understanding where the pieces go, I'm going to go -2 plus log base 5 of 22. Now if you want to type this in your calculator, remember you are going to have to do the change of base in here. So this tells me then that x is equal to -2 plus the log of the tall, or log of 22, divided by the log of the short, or log of 5, and this is approximately equal to a -0.794. A classic example when solving exponential log equations stems from a real-life situation called Newton's law of cooling. Now, Newton's law of cooling says that when we have temperature T of a cooling substance at a given time T, which is typically measured in minutes, can be modeled by the formula temperature equals T sub 0. Now, the subscript of 0 means that this is our initial temperature, minus our room temperature. So we're going to take the change in the 2, multiply it by e to the negative RT. R is going to be your cooling rate constant. T is again going to be your time in minutes, plus your room temperature. And you'll see here in our next example how we can use this. So for example 4, it says you are cooking stew. When the stew is removed from the stove, the temperature is 212 degrees Fahrenheit. The room temp is 70 degrees Fahrenheit, and your cooling rate is 0.046. We want to find out how long it will take for the stew to cool down to 90 degrees Fahrenheit. So if you start out by identifying what every piece is, when we want to know how long it will take for our temperature to cool down to, we know that this is our temperature. We're given that our room temp is 70, or T sub R, and when we remove our stew from the stove, it's at an instant temperature of 212, or this would be our initial temp, or T sub 0. So now by plugging into the formula, we have 90 degrees is equal to our change in temp, or 212 minus 70, times e to the negative, our R was 0.046. We do not know what our T value is, but we do know that our room temp was 70 degrees. So now our ultimate goal is to find this T here, or the time that it takes for this stew to cool down. So in order to start solving for that, we're going to want to eliminate this 70. So I will subtract 70 from both sides. And by doing so, we end up with 20 is equal to 212 minus 70 will give us 142, e to the negative 0.046t. Now we need to go about getting this piece by itself, so I can divide by that 142, and when I divide by 142 on both sides, 20 divided by 142 is actually going to reduce down to 10 over 71. You don't have to reduce this, but it might just make your calculations a little bit easier. And this is equal to e to the negative 0.046t. Now in this case, I need to cancel out my base e. And if you recall, the only way that we can cancel out a base e is if we take the natural log. If I take the natural log of the right side, I must also take the natural log of the left side. Now, for those of you with a graphing calculator, when you type in the natural log of 10 divided by 71, I would highly recommend that you use the storing feature. The storing feature should show up, I believe it's on the left-hand side of your calculator. I will go over this with you in class, but it's just going to make your numbers work out a little bit nicer because it's an exact number. So in the meantime, we're going to take and type in the natural log of 10 divided by 71. And if you remember, natural log and e are going to cancel. So we have the natural log of 10 divided by 71 is equal to a negative 0.046t. And now I can go ahead and solve for t and say that t is equal to the natural log, or if you store it, use the variable that you're storing as. And I'm going to divide that whole quantity by a negative 0.046, and what you'll find is your temperature is your time is approximately equal to 42.6 minutes. And you could probably even round that up to 43 minutes if you'd like. Now our next few examples are going to be similar to the first three. However, instead of using a power, now we're going to be given a log. So for example 5, it says to solve log base 4 of x plus 3 equals log base 4 of the quantity of 8x plus 17. Hopefully you recognized right away that I'm doing a log base 4 on the left and a log base 4 on the right. So again, in order for these two to be equal, that means that x plus 3 must also equal 8x plus 17. So x plus 3 equals 8x plus 17. So because of this scenario, all I have to do now is solve for x. So I'm going to go ahead and subtract x from both sides. This gives me that 3 is equal to 7x plus 17. I will subtract 17 from both sides, and I find out that 7x is equal to a negative 14, and x then is equal to a negative 2. And you can go ahead and plug these in to verify if you'd like. In example 6, this is kind of similar to that example 2 that we did. Sometimes it's not practical, or you'll see in this case where we don't have the same log on both sides. So in this case we have log base 4 of the quantity of x plus 3 equals 2. And if you recall, the only way that we can eliminate a log base 4 is if we have a power with a base 4 as well. So in order to eliminate that log base 4, we are going to do what we call exponentiate. Okay, and by exponentiate, what we're going to do is we are going to take this and make 4 the base of our power. So I have 4 to the log base 4 of the quantity of x plus 3. But if I do that on the left, I must also do that on the right. So what's going to happen is my 4 and my log base 4 are going to cancel, leaving me with x plus 3. And then on the right hand side I have 4 to the second power, or 4 squared, which is 16. So now I'm left with the algebraic equation where I have x plus 3 equals 16. When I subtract 3 from both sides, I am then left with x equals 13. And last but not least is example 7. Now, example 7 is going to be a little bit different in the fact that when you are coming up with your solutions, you should always go back and double check to make sure that your solutions are truly solutions. Remember, sometimes we can get a solution that we can solve for algebraically, but it doesn't necessarily work when we plug it back in. And if you recall, these are called extraneous solutions. And it's incredibly important that we check for extraneous solutions with log functions, since not all solutions will always fall within the domain of a log. And if you recall, you cannot take like the log of a negative number, so sometimes we have to watch out for that kind of stuff. So example 7 is going to deal with this type of a scenario. So here we have log base 2 of x plus log base 2 of the quantity of x minus 7 equals 3. Now back in section 8.5, we learned how to condense, and that's probably going to be your best bet here. So if we take all of this here and we condense this, we have an addition sign here, which tells us that we're going to have to multiply. So we have log base 2 of the quantity of x times x minus 7 equals 3. Now we're in a similar situation to example 6, where we have a log base 2 of some stuff equals a constant. So the only way I can cancel out this log base 2 is if I exponentiate. So I'm going to make a new power with my base being 2 to the log base 2. And I'm also going to have to make 2 as my base over here. So by doing this, my 2's and log base 2's are going to cancel, leaving me with, and I'm going to distribute that x, so I have x squared minus 7x equals 2 to the third will give me 8. So now I have a quadratic equation. So if I set it up as such, I have x squared minus 7x minus 8 equals 0. When I go to solve this, we have x minus 8 times x plus 1 equals 0, which implies then that x is equal to either a positive 8 and or a negative 1. Now if we go back and double check our work, we can go ahead and we'll start out with this 8. I'm going to have a log base 2 of a positive number 8 plus log base 2 of 8 minus 7, or 1, equals 3. Okay, so this is going to work, this is going to work. You can double check. If you condense these down, you'll see that you end up with log base 2 of this plus means you multiply, so I have 8 times 1, or 8, equals 3. And if you use your properties of logs, you have 2 to the third power, which equals 8, and this double checks. Now, when we go to plug in this negative 1 here, we end up with log base 2 of a negative 1 plus log base 2 of negative 1 minus 7, or negative 8, equals 3. The big red flag is going to run in right here, where I have the log of a negative 1, and actually you have a log of a negative number here. Remember, you cannot take the log of a negative number, therefore negative 1 is not a solution, it's rather an extraneous solution. So we will not include it as one of our final solutions. Now if you have a graphing calculator handy, you can also graph this, and you would just have to confirm that x equals 8 is your only x-intercept. So it's at this point in time that we have concluded with section 8.6, solving exponential and log equations. If you have any questions, I will answer them in class tomorrow. I hope you guys have a great day.